Have you ever stopped to think about how a thermostat in your home can just chill and read a steady temperature, but a sensor in your car's airbag system has to react in a fraction of a second? They're both sensors, right? But they live in totally different worlds. Well, the secret sauce is in their mathematical models. It's like the language engineers use to really understand what these sensors are doing. So, let's get fluent in the language of sensors.
All right, here's the game plan. First up, we'll nail down what a sensor model even is. Then, we're going to look at the static model. Think of it as a snapshot. After that, we'll get things moving with the dynamic model. We'll put them side by side to see the differences, and then wrap it all up by looking at why any of this actually matters out there in the real world.
Okay, so let's start at the very beginning. What is a sensor model? At its heart, a sensor's job is pretty simple. It takes some physical thing, like temperature, light, pressure, and turns it into an electrical signal we can actually use. A sensor model is just the language we use to describe how that conversion happens.
To get a little more specific, it's a math equation that describes the relationship between what goes in and what comes out. And you know, this isn't just for textbooks. These models are absolutely vital for engineers. It's how they can predict a sensor's accuracy, its speed, its whole personality, really, before they even build it into a device.
Now, all these models basically fall into two big buckets, and the difference between them? It all comes down to one critical ingredient: time. Static models are what we use when the thing we're measuring is holding steady. Dynamic models, that's when things are changing. That's it. That's the fundamental split we're going to dig into.
So let's kick things off with the static model. The absolute best way to think about this is like taking a photograph. It just captures one single steady moment in time. It tells us how the sensor behaves when the input has settled down and isn't changing anymore.
And the math behind this? It's about as simple as it gets. Y equals some function of x. The output is just based on the input. We're completely ignoring any kind of time delay or inertia. All we care about is that final steady relationship.
Now, for a ton of sensors out there, that relationship is just a nice, simple straight line. And you might remember this one from school. Y equals kx plus b. It's an incredibly powerful little equation that can describe a huge range of common sensors.
So let's break that down. Y is the electrical output we're reading. X is the physical thing we're trying to measure. Temperature, pressure, you name it. A little bit of engineering jargon for you. This is often called the measurand. K is the sensitivity, basically how much the output changes when the input changes. And B, that's just the offset, or where the sensor's reading starts when the input is 0.
And what's so useful about this static model is that it lets us figure out all the key specs for a sensor. We're talking its range, its accuracy, its sensitivity, all the important stuff. It gives us a complete performance profile, but only as long as things are holding still.
Of course, the real world rarely holds still, right? And that is exactly where the dynamic model comes into play. If the static model was a photograph, then the dynamic model is a full-on motion picture. It describes how a sensor reacts over time, because in the real world, sensors are never truly instant. And there's a reason for that delay. It's just physics. Things have mass, or inertia, or what's called capacitance. A dynamic model takes all that lag into account, and it usually does it with something called a differential equation. That sounds fancy, but it's really just a way of describing how things change through time.
We can kind of organize these dynamic models by how complex they are. The simplest is what's called a zero-order model. That's a perfect, ideal sensor with absolutely no delay. Then you have the first-order model, which is by far the most common one you'll see. And finally, there's the second-order model, which you usually find in mechanical systems.
And this right here is a really important point. Most sensors you're ever going to encounter, from thermometers to gas detectors, act like first-order systems. Why? Well, it's usually because they're limited by just one single thing that stores energy, like the physical bulk of a thermometer that needs to heat up. That one bottleneck is what makes their behavior so common and so predictable.
So here's what that first-order equation looks like. Now hey, don't let that dy by dt part throw you off. That's just a little calculus that means how fast is the output changing right now. The really important new player here is that little squiggly tau symbol, which is tau. This is the time constant, and it's everything. It basically tells you the sensor's reaction time.
A perfect example is just a regular old thermometer. When you take it from a cold room to a warm one, the reading doesn't just instantly jump. It climbs gradually, right? It follows a smooth curve. Well, that curve is defined by its time constant. Thermocouples and gas sensors do the exact same thing.
And then, real quick, we have the second-order model.
This one pops up when you have systems with stuff like mass and springs. Think of an accelerometer or maybe a pressure sensor that has a little flexible diaphragm. These things can actually overshoot the real value and then kind of wiggle a bit before they settle down. It's that more complex motion that this model is built to capture.
Okay, so we've looked at both types. Now let's put them right next to each other to really hammer home the differences.
This table really just says it all. Over on the left, with the static model, it's all about the steady state. The input is constant, the math is simple algebra, and time isn't even part of the conversation. Now look to the right. The dynamic model is all about change. The input is varying, the math is a bit more involved with those differential equations, and the whole point is to understand how the sensor responds over time.
So, after all that, why do we care about this math? What's the point? Well, because this stuff directly connects all the theory to how we actually build the technology that, runs our lives every single day.
You'd use a static model when you're doing things like calibrating a sensor or figuring out how accurate it is under stable conditions. But you absolutely need a dynamic model to figure out if a sensor is fast enough for a job. Like that airbag sensor we keep talking about. Its response time is a matter of life and death, and only a dynamic model can tell you if it's up to the task.
So the real takeaway here is that you need both of them. It's not one or the other. Together, these two models give you the full, complete picture of how a sensor is going to perform, both when things are calm and when things get crazy.
So I'll just leave you with this little thought experiment. Grab your smartphone. It is absolutely jam-packed with sensors. Which ones, the accelerometer that flips your screen, the light sensor that dims the display, the GPS, which of those would be totally useless without a dynamic model to describe how they work? The answer to that tells you almost everything you need to know about how our modern world is built.